Okay, so in this video we're going to talk a little bit about orbitals and electron configurations and how you would do them, as well as a little bit of the details about the orbitals. One thing to remember is that there are 4 different types of orbitals before we get into sort of the nitty-gritty details of this. There's the s, p orbitals, d orbitals, and f orbitals. One of the things to remember about these is that each orbital or each orbital subtype will hold 2 electrons. Okay, and so for the s orbital, which there's just one, it's a sphere. Again, remember you can look at any of these, just do a search on Google Images or look in your book. But a set of orbitals, there's only one type of s. So a set of s orbitals is just one orbital. P orbitals, however, there are 3. There's one in the x, one in the y, one in the z direction. D, there are 5. F, there are 7, and therefore the number of electrons at a given energy level, or n, okay, the principal quantum number. So for the 1s, you can hold 2 electrons as well for the 2s, the 3s, the 4s, etc. For the p, which starts at quantum number 2, level 2, you can hold 6 because there's 2 in each of those. A set of d orbitals can hold 10, a set of f orbitals can hold 14. We'll see in a little bit. That's the sort of layout of the periodic table. Therefore, you can look at the periodic table and pretty quickly figure out what you're looking at. Okay, so if we look at the arrangement of these orbitals, one of the important things is that in general s orbitals have a lower energy than p, which have a lower energy than d, which have a lower energy than the f. And if you look at it, this is going to be the order in which you fill. Okay, you're going to start at the lowest energy. The first electrons to go in are going to go in at the most stable, lowest energy, and that's down here, the 1s orbital. The next one up is the 2s. Okay, so 2 electrons in each one. So elements hydrogen and helium, which have 1 and 2 electrons respectively, are going to just put those electrons in the 1s orbital. As we move up to lithium with 3, it's going to start filling the 2s. Once those are filled, you're now going to go to the 2p, which is, you can see, the next highest, and then the 3s, and then the 3p. Now there's a little bit of an oddity here. The d's come in at 3 as well, but 4s is actually a lower energy level. And in a second when we go on the table, that'll be a lot easier to remember that way. Okay, and the 3d therefore fills after the 4s. So the reason of the order of filling that we're going to sort of deal with here, and the reason we're going to label these things, and they're not always going to be s in front of p is in front of d in front of f, has to do with what the actual energy levels of those orbitals are. So one handy way to remember this is if you write out that at n equals 1 through n equals 7 down that way, you'll see right here that you would start with the 1s. That's the only orbital at n equals 1. N equals 2, you have a 2s and a 2p. Then you have a 3s, a 3p, a 3d. And at 4, you have a 4s, 4p, 4d, 4f, and so on and so forth. If you were to write this out in order, pretty simple like that, and draw diagonal arrows through it, you can see that you're going to go from 1s is the first one you fill. Then you come and you do 2s. And then the next one is the 2p followed by the 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, and so on and so forth. So this is sometimes a handy shortcut to be able to write it out quickly, draw the lines, and remember the order at which it goes. A little bit better way to do it, though, is using the periodic table, which we're going to look at next. So if you look at the periodic table, one of the key things to recognize is that the way that it's diagrammed, right, these first 2 columns here are really the s orbitals. And the reason for that is everything on the periodic table, remember, was arranged in terms of periodicity, sort of repeating order again and again, and it has to do with their chemical behavior and how they act. Right? All of the ones in the first column here all tend to form +1 ions. Well, if you take a look, that's because they all have 1s electrons. For hydrogen, it's 1s1, lithium, it's 2s1, and so on and so forth, potassium, sodium, etc. If you look at the middle section here, the transition metals, they're all in this D block. Okay, and that's the 3D, the 4D, the 5D, the 6D. And the P block is right here. You have 2P, 3P, 4P. The F's right here, okay, they insert right sort of after the partway into the 5D. The advantage of this system of knowing that it counts based on essentially the row that you're in on the periodic table is that the atomic number will tell you in what order to go. You just follow atomic numbers. So if you're doing electron configurations, you're going to start with 1s and do that. And then you do 2s, 2p, 3s, 3p, 4s, 3d, 4p. So you just follow from left to right across the rows up until you hit whatever element you're looking for. So if you were looking for the electron configuration of one of the elements that ends in the 4p here, you know that you're going to look at your table and say 1s, 2s, 2p, because I'm in row 2. Next is row 3. There's an s, and then there's a p. Then row 4, there's a 4s. Here's a d. We have to know that the first d is 3. That gets a little confusing, but we can do with that. And then 4p. And we end wherever you are. So that's simply, this is a handy chart to look at. I've also posted it up on our course page. You can look at any point in time. It's in the book and can be found in numerous other places online as well. So in the next bit, I'm going to go through a little bit how you solve a couple of these as examples. Okay, so here's an example of a problem. Write the complete and shorthand electron configuration of bromine, which I've given you. Here is atomic number 35, just to make it a little bit easier for you to find. So let's do the complete first. So if we look at bromine, okay, we're going to it's 35, so the first ones we're going to have to fill, we always have to start at the top. So first orbital we have is the 1s, as we go to hydrogen and helium, so that's going to be 1s2. And then we're going to go to the 2s, that will have 2 electrons in it, 2. Then we go to the 2p, that's full, so that'll be 2p6. And then we go to 3s2, we come across, we now hit the 3p, 3p6, and then we get to the 4s2. Now you'll see that we're at the D block. Okay, we need to remember that the D block begins with the 3d, so it goes 3d, 10, we're going to completely fill that, and then we come back, we're at the 4p now, 4p, and you can review the previous chart if you need to sort of see that again, and we count across 1, 2, 3, 4, 5 to get to bromine. It's neutral right now, so that is 4p5. If it happened to be Br minus, where it had an extra electron, we would then call it 4p6, and now you're starting to see why you would form bromine minus, why it's typically a -1 ion, because that will fill the last spot available in that 4p orbital set. Okay, so the shorthand electron configuration accounts for the fact that everything in that row of bromine is identical up through 3p6. In other words, if we look at the table and picked potassium, it is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Okay? Calcium would be 4s2. Scandium would be 4s2, 3d1, etc. So only these things after 4s on are going to change for anything in that row. And since this 1s2, 2s2, 2p6, 3s2, 3p6 is equal to the last noble gas that we hit, that's the way we write our shorthand. So for bromine, our shorthand would be the last noble gas we hit, which is these, so that's going to be argon, number 18, and then it'll be whatever's left, so 4s2, 3d10, 4p5. So you can see why we would want to do this, right? This will get a lot shorter to do in the shorthand, rather than writing out 1s2, 2s2, 2p6, 3s2, 3p6, etc., for everything. Okay, so now we can see we have a slightly more complicated problem because we're going to have to deal with an F block. Write the shorthand electron configuration of lead, which is element atomic number 82. So the electron configuration of lead, number 82, we look for the last filled noble gas, which in this case is number 54, xenon, on the row above. So it would be xenon in parentheses. And now we're going to have to fill these different states. So first thing we're going to fill here will be the 6s, 6s2. And then if you follow the numbers, 56 is barium, 57 lanthanum, then it goes 58, 9, 60, so on and so forth. So we're going to end up filling the F block, the first of those F blocks. So that is going to be 6s2, 4f14. Now we finish off the D, And remember the D starts at 3, so you can count down 3, 4, 5, right? So we're in the 5D, 10. And now we have the 6P, 2. So that's how it is. Sometimes you'll actually see it written and arranged in the form such that it goes in order of the principal quantum number. So sometimes you'll see books list it as 4F14, 5D10, 6S2, 6P2, and that's fine as well. For my class, I'm going to sort of tell you to go in this way so that you're following the order across the table. Makes it simpler. In all cases, it's probably easier to do that first and then circle back. Also, for the purposes of our class, we're not going to have to worry about what happens if you stop in the middle of an F block. We only have to worry about that with the D block, and we'll talk a little bit about those in a separate video, but some of the exceptions, such as copper and silver, and why there are exceptions and how they change their configurations a little bit.